We're continuing on with section 4.4, dealing with integration and the fundamental theorem of calculus. So in part 1, we looked at using the fundamental theorem of calculus and the mean value theorem for integrals to get us the average over a closed interval. In the second part, we're going to look with the second fundamental theorem of calculus and net change. So when we've been working with these definite integrals, we have our limits of integrations are numbers. But we're saying, what if we have a starting value, but we're leaving the upper bound as a variable instead of a number? So instead of getting a fixed value for this, now we're going to get a function for the area between the curve and the x-axis, but it's going to depend on that upper limit, and we're going to use that as our variable. So one of the things we're doing, again, we're showing here, we have a number when we go a to b of f of x, but here when we're going to a to x, now this is f of t. Notice this is a different variable than this one, because this has to be, let's go back again. This has to be, again, a constant, as opposed when we're looking at this function, because we have to evaluate it there. But, so this is f of t dt. This variable has to agree with this one. This variable is going to agree here. You notice here, instead of getting a number, we're getting a function of x. So, for example, why would we want to use that? Suppose we have this problem. We want the integral from 0 to x of cosine theta d theta for different values of x. What we could do is go ahead and plug in 0 for x, do the definite integral. Not a bad one to do, because cosine has an easy antiderivative. So the antiderivative is sine, so it wouldn't be too hard to do that for each one of these. But our idea here, we evaluate this integral with x up here. As we do that, again, the antiderivative is sine of theta, and we're going to evaluate that from 0 to x. So that's going to be the sine of x minus the sine of 0. That gives me the sine of x. Now I have a function to give me the answer of this definite integral that's a function of x. So I plug in my x value. I can just plug it into here, sine of x, and I can get those different values. This type of a function here we're calling this an accumulation function, because basically as we make x get bigger, we're accumulating more and more area. So this is one advantage of doing it this way, to get that function so we don't have to do a new integration for each interval we do. But you notice we have to keep the starting point the same. So here comes into the second fundamental theorem of calculus. Second fundamental theorem says if we do this integral from a to x of f of t dt, and then we take the derivative of that in terms of x, we end up with f of x. Okay. Yes, really, there's reasons to do this. But one of the ways we're going to look at this, or playing with this, is we're going to look at the net change theorem. Well, I don't know. Wrap this up. The idea is our integral from a to b of f of x dx is f of b, the antiderivative at b minus the antiderivative of a. So, but since f of x, small f, is f prime, because if this is the antiderivative, then the derivative of capital F is lowercase f. We say this. Now, the integral of the derivative is f of b minus f of a. This is going to be what we call the net change of the big function f. So that antiderivative, how is that changing on this interval from 0a to b? So that's our net change theorem. Another one of these lovely theorems. It's pretty much, this is kind of what, it's more of a, this is a use of this integration. If I want to find the overall, that net change, we're kind of see this in action. We'll do an example with this to maybe make a little bit more sense with this. Do a couple of these. So first, at 1 p.m., oil begins leaking from a tank at a rate of 4 plus 0.75 t gallons per hour. How much oil has leaked out by 5 p.m.? Part 2. Get that out of the way. First question is, what does T stand for? We want to make sure we kind of have that defined. I'm going to define T equals hours after 1 p.m. So at 1 p.m. we are at time T equals 0. And then as time goes on, the rate of change changes. So we want to find out how much oil has leaked out. This is going to be my net change. What's the change in the oil? How much is leaked out? So this is then going to be, this is the rate of change. So this is my f prime of t. So I really want the integral. If 1 o'clock is 0, then 5 o'clock is going to be time 4 of 4 plus 0.75 t dt. So we can make that very simply, that's going to be 4x plus, I'm going to write 0.75 as 3/4 because I like thinking fractions. And this is t squared over 2, evaluated from 0 to 4. Why is that an x? I don't know. So why did I prove that either? I'm tired. It's been a long day. So this is going to be at 4. That's 4 times 4 plus 3/8 times 4 squared minus 4 times 0 plus 3/8 times 0 squared, which is 0. So this is 16, and this is 16 here. 8 goes into there twice, so we have 16 plus 6 is 22 gallons have leaked out. Now I'm going to just kind of change this slightly. If I wanted a function, if I wanted to say f of x is how much is leaking out at certain number of hours after 1 o'clock, I would do this integral from 0 to x of 4 plus 0.75 t dt, which is going to give us, again, that's 4t plus 3/8 t squared, evaluated from 0 to x So when it's x, I get 4x plus 3/8 x squared. I plug in 0 just like up here, I get 0. So my function, my accumulation function, f of x, is 4x plus 3/8 x squared. If I wanted to just find out after how many hours, after x hours, how much oil has leaked out, I could use this function. If I wanted to find out between two specific times, I'd go back up to here and do that. Wrong button. So this idea of net change is used a lot in physics. Again, when you're looking at motion of something that's moving in a straight line, and s is the position at time t, and your velocity is s prime of t, then we can say the integral of velocity is going to be the change in position. S of the finishing point, subtract the position of the starting point. And this is what we call the displacement. Now it kind of gets a little confusing on here. We'll look at these questions, because here we're looking at the displacement after 8 seconds. How far did it travel in the first 8 seconds? So kind of, again, an example, if you think about this displacement, we're kind of looking at starting point from the ending point. You talk about my trip to school and back. In a day, I start off at my house. I drive 70 miles to get to school. I teach all day. I get back in my car. I drive 70 miles to get home. My net displacement for the day is 0 because I end up where I started. I didn't move. But I sure traveled a lot. Just look at my gas bill. So that's what we're talking about, the difference between displacement and how far did it travel. So we're going to look at this with a pendulum. It's swinging back and forth and back and forth. So its velocity is going to be, we can describe how fast it's moving, 10 sine t. It's periodic. Pendulum is a good periodic function. So if we look at 10 sine of t, here's the function. This is showing the velocity over the first 8 seconds. Again, we're in radians because when we're doing trig, we will always do radians. So we look at our net change theorem, the integral of from 0 to 8 of 10 sine of t dt. The antiderivative of sine is the negative cosine, so we have 10 negative cosine t, evaluated from 8 to 0. Negative 10 times the cosine of 8 minus the cosine of 0, which will give you 11.46 centimeters. So the net displacement, if we look at from the displacement at time 0 compared to the position at time 0 compared to the position at time 8, the difference in those positions are 11.46. That's the displacement. It's not how far the pendulum traveled, though. So, because we look at this, again, area traveled, we look at the area under this curve, that's positive, but this here is a negative area. So this area is going to cancel out with that area. And so if we get over here to 6.28 seconds, we're going to be back to 0. We're going to be at the exact same space it started, and your displacement will be 0. But you've traveled quite a bit. So if we make that the absolute value, then this will become a positive distance, and we have this distance, we have that distance, we have that distance. So we'd do this with, again, kind of on that earlier problem, we'd break it up into 3 integrals. This one, this is going to give me a negative distance, so I used here with I subtracted that integral. Then we add this one. Again, we could have done it like we did earlier in the last lesson, or the last video, by making this 2 pi to pi. If I switch this, that switches this sign to make this positive. But if I do this, we'll see the pendulum actually traveled 51.5 centimeters, even though the displacement was only 11.46 centimeters, because it's going back and forth and back and forth. There's the fundamental theorem of calculus in all its glory. So have fun with this homework.